very much, Mr. Chairman. First of all, of course, I would like to thank the organizers for this wonderful meeting, honoring Gary, his 70th birthday. And they really did an excellent job. And it's a fantastic campus, nice weather, very good people, nice lectures. So let's give them an applause. Last night I spoke to Gary and he said that getting 70 is not really so bad. So I'm very happy about it because I'm approaching 70 also. As KP Hart then said, everybody is approaching 70. It's true, but it's the interval that is really important. My interval is getting smaller and smaller, and so I'm very happy that somebody like Gary tells me, don't be afraid of it. So now I'm feeling much better. Happy birthday, Gary. Gary has always been one of the top set theoretic topologists in the world. And he specialized in the area of generalized metric spaces. And it has been said already a few times, already early in his career, he found many interesting things about the M1, M3 problem. And as you just heard from Heike, it has not been solved yet, but it has been announced, and so there is exciting news. So maybe this problem is solved now, and then it started so long ago with the work of Gary and of Heike. Not only that Gary cracked fundamental problems, he also wrote many strong and influential survey papers, very good ones. I think the first one was in the Handbook of Set Theoretic Topology, and ever after he wrote several survey papers, very good ones, very easy to read and very well organized. He's also one of the editors of Topology Proceedings, and he's on the editorial board of the journal Topology and its applications. And he's also on the committee for the Mary Ellen Rudin Young Researcher Award, which is really a lot of work, finding all these fantastic people and looking at their thesis. So he's willing to do his share of the work, of the administrative work that goes along with his status. And he's a great referee. And he's always willing to help. I can tell you that some people said here they never saw Gary angry. But if Gary is a referee, I'm sure several of the authors got very angry when they read his report. So he's a very good referee, very sharp, and well, it's the way it is. And to sum up, he's always willing to help, and that's a very good thing if you have that inside of your character. And Gary thanks on behalf of all of us, and we wish you many good years to come. It is the hardest part of my lecture, and that's over. Great. We will now do mathematics, and all spaces that I will speak about will be separable and metrizable. I think there will be one exception, but okay, who cares about that? And for subsets X of the real line, we investigate homogeneity properties of the Edwards type space E of X. So you take the subset of the real line, X. I'm very glad Istvan found this thing that makes the lecture is very much easier. So you take a subset of the real line and you look at E of X. E of X is the Edwards type space that you can build from X. And that is just the set of all vectors X in Hilbert space, in the real Hilbert space, the space of square summable sequences with the standard norm, so that every coordinate of that vector is inside X. That's the Adder's type space that you get from X. Okay, doesn't sound very exciting, I admit it, but it will be exciting, don't worry. These spaces were introduced probably by Hurewicz, possibly by Adders, back in the 40s. And there are two very basic examples of such spaces. The first one is E of X, where X is the subspace of the real line consisting of all the rational numbers. And this is called Adder space. In all textbooks on this dimension theory, you will find this Adder space as a curious counterexample in this dimension theory. And that's called the Adder space. But actually, in Adder's 1940 paper, there were two Adder spaces. Namely, the one you built on the rational numbers and the one you built on the conversion sequence, including its limit. And that Adder's space is a closed subspace of Hilbert space. And therefore, it's a polar space, it's a complete space. This Adder space, if you build it on the rational numbers, you can very easily see it has many closed copies of the rational numbers inside, so it cannot be complete. So this one is not complete, and this one is complete, and therefore it's called complete Adder space. So there were two different Adder spaces in the paper by Adders. And we let E and EC denote Adder space and complete Adder space respectively. E is an F sigma delta space, but not H delta sigma. So it's an absolute F sigma delta space. It's an intersection of countably many F sigma spaces inside every complete space, the way you think it is, but it's not a countable union of G delta sets. So it's a true F sigma delta space, and as I already said, the complete Adder space is Polish because it's a closed subspace of Hilbert space. So, what was the interest in the Adder spaces? The story is that Adders visited Hurewicz when he was in Princeton in 1940. And Adders said, "Do you have a problem for me?" And Hurewicz says, "Yes, I have a problem for you." And Adders came back the next morning and he had solved it. And this is what he did. He proved that if you look at Adder space and complete Adder space, then they are one-dimensional, which is really surprising because if you look at how they are defined on very zero-dimensional subsets, namely the space of rational numbers and the convergent sequence. But if you build them inside Hilbert space, something funny happens.
Of course, they had to explain Adders what dimension it was.
I don't know about that.
I know. That's why I
Okay, good. And also, it's really trivial to see that the square of Adder space is homomorphic to Adder space, and you can also see very easily that the square of complete Adder space is homomorphic to a complete Adder space. So you have a one-dimensional space whose square is also one-dimensional, and that explains the interest Hurewicz had in these spaces. Because Hurewicz had just shown that if you take the product of two spaces, X and Y, all separable metric, and Y is a compact one-dimensional space, then the dimension of X cross Y is 1 plus the dimension of X. So it means that if you take the product of every separable metric space with a compact one-dimensional space, its dimension increases by 1. And so he wondered, is compactness essential in that result? And this example shows it is, because there is a one-dimensional separable metric space whose square is also one-dimensional. So to me it's unclear if Hurewicz already had this example and he asked others, can you prove this? Or that others cooked it up. It's not clear from his paper. After that, so for many years, these other spaces were curious objects in books about topology, but this changed in 1969 with the paper of 3 people that I know very well, Kawamura, Oversteken, and Tim Chetty, and they proved the interesting thing that if you take Adlers's complete Adler space built over a convergent sequence, it's topologically homeomorphic to the Adler space built on the rational numbers. Now, this space is a closed subspace of Hilbert space. This space is dense G delta in Hilbert space, so it's not an obvious result that they are homeomorphic. You must really work on it. And okay. They also proved that the complete Adler space is an example of a countable dense homogeneous space, and it's one of the very few spaces that we know that are CDH, countable dense homogeneous, and not strongly locally homogeneous. Complete Adler space is not strongly locally homogeneous. I will not go into that. Don't worry about it. And they also proved that in that same article that complete Adler space is homeomorphic to the endpoint set of the Lamech fan. It's a very strange fan, and it jumps up and down. And if you look at all the endpoints, and then that is topologically homeomorphic to the complete Adler space. So suddenly, these Adler spaces faces in different areas besides Hilbert space and this dimension theory. And then Dobrovolsky, Grabowski, and Kawamura in 1969 that certain line-free subgroups of Banach spaces are homeomorphic to complete Adler space. A line-free subgroup is a subgroup containing no lines in a Banach space, and certain, I write there because not all complete line-free subgroups of Banach spaces are homeomorphic to EC. But so suddenly they come up in a different setting. And then I proved with Jan Dijkstra that certain polishable ideals on the rational numbers are homeomorphic to complete Adler space. Not in the zero-dimensional topology, but in the Polish topology. Therefore, they are polishable, answering a question that Stevo asked us. And then in 2010, I proved with Dijkstra the following result. That M be at least a two-dimensional manifold, and let D be a countable dense subset of M. And then if you look at the group of all homeomorphisms of M, given the compact open topology, that fixes setwise a countable dense set, that subspace of the group of homeomorphisms is topologically homeomorphic to the Adler space. And we were quite excited about this result because the structure, the topological structure of homeomorphism groups of nice objects is a mysterious area. It's known that the group of homeomorphisms of the real line is homeomorphic to 2 times Hilbert space. That's a result of Anderson. It's known that if you look at all homeomorphisms of R2, that's homeomorphic topologically to Hilbert space. It's a very complicated theorem of Luke and Mason, approved in the 70s. About R3, nobody knows. What is the topological type of the group of homeomorphisms of R3? Nobody knows. No idea. R4, R5, and nobody knows. And then you come up to infinite dimensional objects, such as the Hilbert cube, and then suddenly it's known. The Strunchik and Ferry proved both independently that if you look at the homeomorphism, the group of the Hilbert cube manifolds, they are topologically homeomorphic to Hilbert space. So, if you are finite dimensional, nothing basically is known about these groups, and this is the first result where you at least know something. If you fix the countable density